we are going to talk about partial derivatives of multivariable functions, and we have an easy method to take partial derivatives in such a way that while taking a partial derivative with respect to variable x, we behave the variable y as a constant symmetrically. If you want to take partial derivative with respect to y, then we behave the variable x as a constant. Let's provide an example. Okay, our function is x squared, y squared, z squared. Okay, let's take derivative with respect to x. Then we behave the variable y and z as a constant. So then the derivative of x squared is 2x, and the derivative y squared plus z squared with respect to x is 0. So we have this. And symmetrically, if you want to take derivative with respect to y, you behave x and z as a constant. And finally, if you want to take derivative with respect to z, you have to behave the variables x and y as a constant. So f of fz equals to 2 times z. And clearly the function has two independent variables. Another example, we have a function of three variables x, y, z, and the derivative with respect to x is equals to the firstly you have to apply the derivative rule of logarithm, namely, okay, the derivative of this function over the function xy over z. Yes, and the derivative with respect to x of that statement, here you have to behave y and z as a constant, which means that the derivative with respect to x is y over z over the function f, and after some factorization you have 1 over x, and other derivatives are fy and fz. Those are similar. Another example, fx comma y equals to, this is the inverse function of tangent. Okay, let's say tangent minus 1. The derivative of f with respect to x equals to this statement, the derivative of this statement over 1 plus the square of this statement. As you can see, to take partial derivatives, first we apply the derivative rules of functions. For instance, here, let me write arc tangent derivative equals to, it is better, yes, the derivative of u over 1 plus u square. After applying this rule and the partial derivative, okay, and you can easily arrive to this result and symmetrically. Yes, fy, the derivative of this statement with respect to y. After some calculations, you find this. And you can solve by yourself this problem. And we have higher order derivatives. fxx is successively derivatives, namely the derivative of the derivative with respect to x with respect to x. And firstly the derivative with respect to x, and next with respect to y. Though this is symmetric case, first the derivative with respect to y and next with respect to x, and successively derivatives with respect to y. Those are called second order partial derivatives. And in a similar way, you can define higher order derivatives. Okay, we have a function cosine of 2x minus x squared e 5y and plus 3y squared. And let's find all second derivatives. And for this, firstly we have to find first order derivatives. Let's take derivative with respect to x. And here is depends only the variable x. So we have this statement, and here must be 0. And here e5y is a constant. Of course, v is not constant. We behave as a constant, and we have the first order derivative with respect to x. And with respect to y, we behave this statement as a constant, and this result. And for the second order derivative with respect to x, we take derivative this statement with respect to x. So here this we behave this statement as a constant. So we have this result. And this means that take derivative with respect to x and next with respect to y. So from this equality, we may obtain this one. Of course, we apply some derivative rules that you know already. Okay, and for this, we have another second order derivative. And you may see these are equal. But of course, in specific this example. And we have a theorem, Clarius theorem. Let's suppose that f is defined on a disk, contains the points a, comma b. If the functions are continuous on this domain, then we have this equality. And the functions that we will solve, we will investigate, are all satisfy this equality. Namely, you can always take this equality as true. An example, let's verify the Clarius theorem for this function. Okay, we have to clarify this second order derivatives. For this, first we have to find the first order derivatives. After applying some derivative rules, and we may see that the Clarius theorem is valid. And you can check by yourself for this function. Okay, another higher order, 5th order partial derivative. Okay, as you can see, those are in the form multiplication. So and the order is not important. So you can start from by the variable x or y or z. It doesn't matter. Okay, the first derivative with respect to x is this. And you see, this is the derivative of logarithm. And the second order derivative with respect to x, this statement is the derivative of this. And y, here is a polynomial. So we have this one. And z, we take derivative. And again, the derivative with respect to z, we have final result. We have a third order derivative, and this means that f, y, x, x. But the order is not important. So you can start from the variable x, as you see, and the derivative y, and this statement both includes the variable y. Perform Leibniz rule, and we have this result. Another example. In physics or in mathematics, this equation is called Laplace equation of two variables. And let's prove that this function is a solution of Laplace equation. Namely, the derivatives, the second order derivatives with respect to x and y holds this equality. For the solution, we have to find these derivatives. The finding these derivatives is quite easily. And the replace with the values of these derivatives into Laplace equation. You can easily check 0 equals to 0, which means that this function is a solution of Laplace equation. If you can check by yourself this function also is a solution of Laplace equation. Example, and prove that this function is a solution of this the partial differential equation. For the solution, we have to replace the values of derivatives in this equation. So we have these derivatives, and one is x over square root x squared plus y squared, and symmetrically up to x and y. If we replace the values in this equation, after some manipulations, we have z. So our solution, our function, I mean this one, is a solution, the equation given in example 9. Yes, the three-dimensional Laplace equation, and in the previous examples we have the two-dimensional Laplace equation. Okay, our function is x squared y squared plus z squared alpha. And the question is, if the function that satisfies the three-dimensional Laplace equation, then determine the values of alpha. Which values can take alpha? So we have second-order derivatives. F of x. Okay, you may shift alpha as a coefficient, and inside the derivative of inside with respect to x, which is 2 times x, and the second order, again, you may shift alpha minus 1 as a coefficient, and inside derivative, and we use the Leibniz rule, so we don't touch first place, plus we take derivative of the second part. Yes. By the way, the other derivatives are symmetrically up to x, y, z. Namely, in order to find the second order derivative of f with respect to y, then you have to replace x with y, and similarly x with z in this case. And if you, with the values of derivatives into the three-dimensional Laplace equation, after some calculations, you obtain this equality. In order to satisfy this equality, the alpha must be or 0 or minus 1 over 2. In case alpha 0, you have a trivial solution, namely f, the function f is a constant. So the important solution is the case alpha equals to minus 1 over 2. Okay, we have an important rule for taking derivatives, called chain rule. Let's recall the chain rule for one variable functions. If y depends on the variable x and the x depends on the variable t, then finally y depends on the variable t. So and you may take derivative with respect to t of y by using this formula, and we call this chain rule. And you can extend this rule to more than one variables. So let's define it. Let f be a function and the first derivatives are continuous, and f itself also continuous on this domain B, and the variable x depends on the another two variables u and v, and y depends on the variable two variables u and v. In such a case, as you can see in this diagram, f at last f depends the variables u and v. At the beginning, f depends x and at the beginnings, f depends on the variables x and y, but x depends on the variables u and v, and similarly y depends on the variables u and v. So at last, f depends the variables u and v. So this means that you have to take derivatives of f with variables u by using chain rule. Let's look this diagram. If you want to take derivatives of f with respect to u, you have to include the variable x and y, because both depend on the variable u. What I am trying to say, that when you take the derivative of f with respect to u, you have to apply this rule, and symmetrically with respect to v, you have to perform this. Firstly, the derivative of f with respect to x multiply x with respect to u plus f with respect to y and multiply y with respect to u, and symmetrically the second one. The basic method, the basic argument is this. But we have some special case, and in this we have 4 or 5 special case, and we can extend this basic argument in the following cases. For instance, f depends x and y depend another variable t. So the chain rule takes this form. Yes, as you can see, x and y exist in this equality. Similarly, if f depends x and y and z, and x, y, z depend on the variable t, yes, and the chain rule takes this form, and f depends x, y, z, and x, y, z depend on the variable u and v, then the chain rule takes this form. If f is a function of one variable, but the variable x depends on 2 different parameters, then the chain rule means this form. Okay, some examples. Our function depends on 2 variables, x and y, logarithm x squared y squared, but x equals to this and y equals to this statements. So x and y depends another 2 variables, which means that w depends both on u and v. Okay, and in order to take derivative of w with respect to u, you have to you may use the chain rule, and after some calculations you may find the derivative is equal to 2, and symmetrically you may find the derivative of u with respect to v is equal to 0. There is another way which is not wrong from a mathematical perspective. The way is replace the values of x and y in the function directly. I mean, if we do that, then we have logarithm. You see, if we replace x with EU cosine v and y equals to EU sine v, we obtain e 2 times u, because cosine squared plus sine squared equals to 1. Then, which means logarithm and e, we have 2 times u. So the derivative with respect to u, let's say u, the derivative of w with respect to u is equals to 2, and with respect to v, see there is not any variable b, so we behave the function whole constant, so we have 0. This is another way. I think it is simpler. Okay, we have another function, a logarithm x square plus y square plus z square, and x, y, z depends on another parameter t. Then the chain rule takes this form, and after some calculations, you may find this. So, and in second way, if we replace with the values x, y, z in the function f, you obtain ft equals to logarithm 1 plus t square. And you have to take some derivatives, or directly the derivative t, you obtain the derivative of f equals to times t over 1 plus t square. Yes. This is another way. This example is similar to the previous one, so we can omit them and some problem to solve yourself. This is another similar example. So I pass this. You can check already these calculations and some problems to solve yourself. Okay, this is a different example. Let's provide it. Z depends on x and y, but x and y depends another two parameters, u and v. So the chain rule takes the basic form. So after calculations, we might find this and another derivative this. Yes, some problems. We have a function f depends on UVW and UVW depend on three parameters x, y, z. So we have to check the sum of these derivatives is 0. Okay, f depends UVW, but UVW x, y, z. At the end, f depends x, y, z. In order to take derivative with respect to x, you have to include the variable u, because u depends on x, and you have to include the variable w because it includes the variable x. So, not necessary to include the variable v into your calculations. You may omit this because already the derivative of v with respect to x is 0. Okay, after taking derivatives, you may find this and symmetrically this one. As you can see, if you sum 1, 2, 3 equalities, you may easily conclude the sum is 0. Okay. This is a very easy example. If you replace with x and y with cosine t and sine t, you may obtain u is a constant function, 1, and the derivative is clearly 0. Okay. In this text, there are many problems that you may solve yourself, and please do that. Okay, we have another section, total differential, which is important. Let's recall the differential of one variable function. Let f of x be a one variable function. Then the differential of f is defined by this equality, namely the derivative of f with dx. Dx indeed is an amount. Yes, namely is a number. But the number of replacement on the axis x-axis. Yes, then the differential of y, namely the differential of function f, is a multiplication of the derivative of f with respect to x with the number dx. Dx is a replacement on the axis, on the x-axis. Okay, for two variable function, the differential, the word of differential is replaced with the total differential, and is defined the derivative of f with respect to x multiply dx is a number plus fy dy. And similarly, if your function is a function of arbitrary variables, then the total differential may be extended such a way. So let's find the total differential of this function. In order to solve this example 1, you have to find the first order derivatives. The function is quite simple, and you may obtain the total differential as in this equality. Okay, another example for finding total differential of such a function at the point 1, 2, 3. So we need to take derivatives of first order. We have a polynomial function which is simple, and we find this. If we replace x with 1, y with 2, and z with 3 in this equality, then we obtain 8dx plus 2dy and plus dz, which is the solution. By the way, the total differential we defined is of first order, and we may define second and third or the general order total differential. Let's see to this example our function x, y, z, and let's find the third order total differential. Okay, we have this already defined. And for the second order derivatives, let's write df as I okay excuse me, yes. If we perform again the differential to I, we write ix, iy, iz. So if we replace I with the value of I in this equality. So we have the second order total differential. And for the second order derivative, if we perform in the previous way and we obtain this one. As I said before, dx, dy, ds are the numbers, are the constants. Okay. We have some applications of the notion of total differential to some previous example. For instance, let's consider a cone whose height is 30 centimeter. The radius of basement is 10 centimeter. And the problem is, if h is increased by 3 millimeter and r is decreased by 1 millimeter, then calculate approximate change in its value. Of course, you may solve this problem by a certain result and using some computer programs, but without computer programs, you may also this problem approximately obtaining approximately a result by using total differential. Okay, the volume of the cone is given by this formula, and the parameters are the radius and the height. So let's say r and h. Okay. The total differential of the volume function is the derivative with respect to radius multiply dr, and with the derivative of the volume with respect to h multiply dh. By the way, the change is an decreasing in radius and an increasing in height. And if we replace dr represents the replacement in the of the variable r, which means that we replace with dr with the minus 0,1, and similarly we replace with dh with 0.3. Also, we replace with h with 30 and the r with 10, then we obtain minus 10 pi. So the total differential is minus 10 pi, and which means that the volume of cone will be approximately decreased by 10 pi centimeter 3. Another example, let's consider a rectangle, and edges are 10 and 24. If this edge is increased by 4 millimeter and the b is decreased by 1, then the question is the change in the length of diagonal side of this rectangle. Okay, the diagonal side of this rectangle is, let's say, L. The L is equal to the square root a square plus b square. Okay, we have these equalities because the hypothesis of the question like that, and this is the formula of total differential. If we replace the values of the derivatives in this equality, okay, then we obtain 0.062 centimeter, which means that the diagonal side will be increased approximately by 0.062. Okay, another example is calculating approximate value of this number. So if the question was 1 over 3, so we have nothing to solve. We have 1, but and here is the power, here is the base. If you increase the base by this amount and the power, if you increase the power by this amount, of course the result must be greater than 1. But what approximately? Okay, we have in this we have a function. We have a function x, y, and we have to find the total differential of this function. Let's find fx dx, fy dy, and in order to take derivative of f with respect to x, you have to behave the variable y as a constant, which means the derivative is this, and symmetrically you have to behave the variable x is as a constant, so the derivative is this. And the final, if you replace x, dx, y, and dy with these values, you obtain 0.06, which means that we say that this is clearly greater than 1, then here is equals to approximately 1.006. Yes, and you see at the diagram, yes, x, 1, y, so the result is 3. The result is 3, but what happens to, in this case? The point is that there's some problems. You may solve yourself. Okay, the implicit derivatives of two variable functions. Let's recall the implicit derivative of one variable function. This is the explicit form. Yeah, let's say the y depends on the variable x. This is the explicit form, but this is the implicit form. For the implicit derivative of one variable functions, we have already this formula from the first semester of this course. So let's see to what happens in two or more variables. Okay, and z is a dependent variable on x and y, but the z is not given in explicit form. The z is given in implicit form. Then our formula is like that. So this is very simple. Let's behave x and y and z are independent variables. Then, by using the chain formula, let's take derivative with respect to x. F of x, fx, but the z depends on x and y. Let's write here zx, okay, and plus f, the derivative of f, capital F, with respect to z, equal to 0. And with respect to y, we write here f y, zy, and plus fz. By the way, let me make more clearly. F of z. Here is excuse me. I will. Okay. By using the chain formula, let's obtain this. We write the derivative of f with respect to z and multiply z of x plus f, the derivative of f with respect to x equal to 0. Then we obtain this equality from this equality. And symmetrically, we may obtain this by using chain formula. Okay. As you can see, the function z is not given in explicit form. So, to take derivative, we have to use the implicit derivative rules. Namely, first we have to take derivative with respect to of f with respect to x and z, and we replace the values in this formula. And after doing this job, we obtain this equality. So, but the question is given at this point. So we replace with x is 0, y minus 1, z 1. Then we obtain this. And similarly, another derivative. Okay, another example. We may obtain derivatives of z with respect to x and y by using the implicit derivative formula. I mean these equalities and these equalities. So the derivatives are simple, and you may obtain easily these numbers. And the another examples are similar. So you may solve these examples by yourself.